And I'm very happy to announce first one of our best paper winners. So it's a paper on parallelizing multi-objective A-star search, and it's going to be presented by Saman Ahmadi.
Thank you. Okay. Hello, everyone. Good morning. My name is Saman from RMIT University in Melbourne. And today I'm pleased to present our work on parallelizing multi-objective A-star search on behalf of my co-authors, Nathan, Andrea, Daniel, and Mahdi. Okay, so what is the problem? So we're solving the multi-objective shortest path problem. So the difference between multi-objective and single objective is we have multiple objective or cost per edge of the graph. So here, for example, we can have up to d edge cost, and in particular, we're interested in objectives more than 3. If we have 2 objectives, the case is treated as a bi-objective, which has its own literature. So here, the task is to find a set of Pareto optimal path for a given start goal states in the graph, such that there is no path in the graph offering better cost than what we have in the solution set. Here we have a toy example. Assume we have 3 paths from this from S to T. So you see their cost vector here. So none of them dominates the other one in terms of cost we have. Excuse me. So, and if we assume these 3 paths are better than all other paths in terms of all objectives in the graph, so we have these 3 as the final solution set. So this has a wide range of applications, as in like transport. One example, one application is, for example, planning quick bike and pedestrian-friendly path for people with disabilities, which appeared in AMS 25. And also recently we managed to get some applications in graph theory where alternative path you want to determine in case of failure is chosen from a Pareto set. Okay, so what is the state of the art? The state of the art is using A-star. So as you know, in A-star, we need to build some heuristics. So A-star works with heuristics. So the heuristics we have, if you have d number of objectives, so we need to build d heuristics. For each individual objective, we can do some backward searches to build perfect heuristics. So we have the backward searches here. So once we get the heuristics, we insert initiate a start node and insert that into the queue, and then start exploring everything from start to goal in best first order. So as you can imagine, best first order is G plus H, where G is the cost of the path from start to the state, plus H, which is a lower bound or cost estimate from the state to the goal. And then we add them up, so we get some F values. These F values are the total estimated costs from start to goal through that state. So we have D of them, so we have a cost vector for F. So we can do this and stop when there is nothing in the queue to explore, but there are some dominance rules. So for dominance rules, I have one example to show how it works. So imagine we have like three paths from start to A. So we want to actually see how dominance works. So we have a heuristic from A to goal. So these are the values for heuristics, and we have one solution which acts as the upper bound. So node number 1, first path to A. So we get cost. So we have cost here, and also lower bound. So this gives us F values. So then we check the F values of this with the solution. So we see, well, for this path, so what we have is this path, this node is not going to be dominated by the solution because we have its second cost smaller than the solution. So it gets expanded. Then we have another node number 2 with 11 and 6 as the second and third cost. F1 is increasing. This is what we have in A-star. 11 and 6. 11 and 6 are the F2 and F3 values. So we check against the upper bound. This is out of the upper bound, and then we can prune it. Next one we have node number 3. This node has 9 and 8 as the F2 and F3 value. So this is not dominated by the solution, as we can see, because 9 and 8 is within the bound. 9 is within the bound. But 9 and 8 is dominated by the previous solution, so previous node number 1. So this is not dominated by the upper bound, but it is dominated by node number 1. So it is not going to expand it. So multi-objective with A-star works with dimensionality reduction. As we observed, every time we explore, if one value is monotonically non-decreasing, so one key aspect is we can get rid of the first dimension and do all the pruning all the dominance check, all calculations based on the truncated vector, which is F2 to FD. In this simplified things, and I speed up the search. But there's still a challenge. So what is the best order if we want to do multi-objective A star search? We can have F1 to FD searches, right? So one can start with F1 to FD, one can lead the search with F2, one can lead with F3. And the observation is we may get different performances if you start with different objectives. Okay, so what we can do in terms of contribution to this field. So we thought perhaps we can parallelize the search. We do a bunch of searches. If you have D objective, we do D runs of multi-objective A star, each of them on one order. So the first one here, for example, we employ highest D number of threads, CPU threads, and we give the first thread the search on F1. So the search A star search on the first thread is led by F1. The second one on F2, third one on F3, and all the way to D, led by FD. Okay, easy. So this is a sneak peek of the results. Let's see how it works if you do this naive parallelization. So I have here the number of solved cases per the runtime. So so you are better to be in the lower the better, right? So we solve more cases in limited time. So the top curve you see is like the conventional multi-objective A star if you do like the F1, F2, the conventional ordering, whatever it is, like F1, F2 is the base. The bottom one, this curve, is what if we had the best possible orders. So we have a virtual oracle that tells us if you do F1, if you do F3, if you do F4, if you have four, like here we have like 4 objectives. If we do 4 MYA stars and give the and store the best performance of these four runs as like the virtual best, then this is the best we can get out of these 4. Okay. Now I want to see where the naive parallelization sit. Here's the result. So the naive parallelization is somewhat better than the conventional ordering, but doesn't catch the best ordering. And this is mainly because of the huge overhead we have and the significant overlap between the searches, between the threads. So we want to catch the best virtual oracle. Okay, so we have 2 options to get rid of the huge overlap. So one option is what if we build a solution pool. All the solutions of different threads are stored in one pool, and every time we want to expand something, we can go through this list and see, okay, we have all the solutions, best upper bounds available, and then check them one by one and prune. This is good. You never generate any duplicate solution, but this is very expensive to compute and almost impractical. So the other way to deal with it is perhaps we can take some partial information. So the downside is we may produce still some duplicate solutions, because when you run multiple searches on the same thing, it is possible in the worst case all of them compute the full Pareto front, and you have like D copies of the full set. This is the worst case you can get, but we want to minimize that. So we still have perhaps some duplicates if you use partial information, but hopefully that would be less expensive. So we did this, actually we tried this for bi-objective search, which is somewhat relevant to this. So in bi-objective search, as you can see, we have, if you have just 2 orderings, 2 possible orderings, F1, F2, F2, F1, if this is my Pareto front, one of the searches explores from the top left corner, and the other one explores the searches from the bottom right. And at some point they meet, and we can guarantee that we will never generate any duplicate solution. But this is not the case in multi-objective search, because that's far more complicated. We won't have some of the rules in bi-objective search. So instead of just going through the pseudocode, I have one example to see how we get rid of this issue. So here I have the 4 objectives. These are the solutions I've discovered in thread number 1. This is just for thread number 1, and we can replicate that for other threads. So I have, like, say, 5 solutions so far discovered. In multi-objective A star, we do 1 truncation. This is a truncated vector of these solutions, right? Nothing new. This is what we know. These are all non-dominated. None of them dominates the other one. Okay. A new solution arrives. This blue one is my new solution. Okay. This is non-dominated. I again do 1 truncation. I have a new set. I have just 1 new solution. I check the previous one what to have. Okay, it seems the new solution now dominates the very first one, because you see it is better than the top one in all aspects. So we get rid of that. So we still have 5 things to do. So okay, this is all you do in multi-objective A star, and this is where you go. You won't go beyond that. But this is still very loose upper bound. Why? Because every solution, every node you get during the search, you need to go through these upper bounds one by one, check 3 objectives to see if that new node is going to be dominated or not. If not, then you expand it. Okay. So, and now this is where the magic happens. We see, okay, perhaps we can still use some information from the other threads and make these upper bounds even tighter. So the maximum truncation we do in a multi-objective A star is just one truncation. To further improve this, we say, okay, we are actually having lots of information from other threads. Let's see what others are doing. So I see this truncated vector is led by F2, right? I ask the second thread, hey, second thread, where are you up to? Second thread responses back that, hey, I'm exploring F2 values of 6, meaning that whatever I'm going to expand has F2 value of 6 and more. So I can look at the list. It seems I have 1, 2, 3 upper bounds with F2 value is smaller than 6. So we have these 3, 4, 5. So just take them and do one more truncation. This is a valid truncation. Why? Because for any solution dominated by this new upper bound, it has only 2 cases. Either its F2 value, for example, F2 value is smaller than 5 or larger than 5. If it's larger than 5, it is immediately dominated by this. Obvious. But what if it is smaller than 5? If it's smaller than 5, so it's not going to be dominated by this, then what happens? If it's not going to be dominated by this, because we know that the second thread is doing a complete search, and the F2 value is smaller than 5 falls within the explored range of the second thread, right? We can guarantee that that solution must have been discovered in the second thread. So even if F2 value of any solution dominated, pruned by this is smaller than 5, there is no worry. We can guarantee that it is somewhere else. Not in thread 1, but hopefully in thread 2. So this is valid. Now we have like three tighter upper bounds. And now we can see, well, this new truncated vector is now dominated by the blue one. So we got rid of one of the upper bounds. Now we have far tighter. So this is not the end. We do one more. Again, we say, okay, this is now by F3. Let's ask the other thread number 3, what it is doing. So we get the upper bound, the lower bound of 7 for that one. We again check the list here. We see we have this thing smaller than 7. With the same reasoning, we do one more truncation, and now we have a super tight upper bound on F4. So what does it mean? It is very important because now we can claim that anything, anywhere in all of the threads with a F4 value of larger than 8 can be pruned. Compare this single value with the list of like bunch of loose upper bounds. And the other important thing is this F4 value of 8 is now imposing a termination case for this fourth thread, which is run on F4. So we can stop as soon as fourth thread hits F4 of 8. Results, we did some experiments on the NY map of the DMAX challenge for 3 to 5 objectives for the 2 of the leading multi-objective ASR searches. And this is, do you recall this plot that I showed you before? So you wanted to catch this purple curve. But with this upper bound technique, now we managed to get even better. Some factors better than what the best variant, the best virtual best variant could give us, right? So this is great. In terms of detailed results, so well, we solved more cases, we have better runtime, but the interesting part I want to show you here is the speed up we get with respect to the base variant is somewhat proportional to the number of threads we have, to the number of objectives we have. So we get better speed up for higher dimensions. You see, like when we increase the dimension, we have 5 costs, 3, 4 costs, and 3 costs, the speed up increases linearly. But the downside is we need to spend more, we need to consume more space. And this is my last figure. So the speed up we observed in the previous slide is just the average speed up, but we can get up to 1 order for some cases, so this is good. And in summary, we have introduced the first parallel search framework for multi-objective A star, which comes with a unique upper bounding technique that enables dimensionality reduction to 1 and enables constant time pruning. And it's compatible with all existing multi-objective A star solutions and achieves a speed up proportional to the problem size. And for the future work, we aim to extend the framework to more than these threads to see if we can get superlinear speed up with respect to the number of objectives.
Thank you. So we do have time for questions. Yes, Miguel.
Okay, thank you, Saman, for the talk, and congratulations for winning the Best Paper Award. That yesterday I wasn't able because of trade, I understand.
Yeah.
Yeah, well, I hope that
That was unfortunate.
Sorry?
That was unfortunate.
That was unfortunate indeed. But Australia is like that. Waiting for a trade is quite the story.
Yeah.
My question is, in these benchmarks, how often was the case that the optimal solutions for different objective functions were structurally very dissimilar? For instance, they don't share any transitions or any actions, or there's a huge difference in, for instance, in the prefix.
No, so the solutions we have are not that much correlated. So for objectives, they are not that correlated. Okay. Yeah, so they are might be completely different. Okay. Yeah, the higher the dimension, the more difficult the case to solve. Yeah.
I mean, the more probable is that you will have two optimal solutions which are completely different.
Yes, yes, of course, yes.
More questions?
Hi, very interesting presentation. I have a question on so essentially you are trying to find all the dominant solutions. And when you are ordering in the A-star search, when you have a couple of non-dominated solutions, how do you determine the order? Or you rank the objective functions?
So we have a priority queue. So ordering is actually following this. So we might have, so if we are ordering, if we set the ordering, and then priority queue actually the first element of the vector has higher priority.
Then I have a follow-up question. Then what's the difference between you treat this whole order objective as one lexical ordered one objective?
So you would lose optimality. So if you have this one objective, if you combine them and get one objective instead, something like that.
Yeah, and treat that as lexical ordering,
yeah, you can do that trick. This is the implementation trick. You can do that. Oh. But basically, what we want here is having this F1 leading the search, because this has a higher priority. Okay. Everything is ordered based on this F1 in the conventional MOA star.
Okay, we have time for one more question. Yeah.
Thank you for the talk. So you mentioned that you could go up to more than D threads.
Yeah.
And having D threads get you tighter bounds. How would you get tighter bounds? Is it partitioning the state space somehow? Can you give a little bit?
So the challenge is with more than D threads, we would have at least one of the threads running on the same F. So for example, with the different threads, we have from F1 to F2 distributed. But if you go one more, one of them would be like a duplicate on F2, but they might have different ordering for the rest of the objectives. That's a challenge. I still don't have any solution to that. That's my future work to get rid of, to somewhat resolve the case with more than D threads, because one of them would definitely be duplicate. Yeah.
All right, so let's thank the speaker again.